This is a demonstration of the partially completed controller cards, and I'll start by giving an overview of the cards themselves. As with the sequencer in my last video, it's cards plural, as a controller is made up of two cards stacked together. And as before, having two cards allows a controller to get at the full range of connectors that it needs to do its job. But also, there'll eventually be way more relays than would ever fit on a single card. For the moment though, the controller only has a handful of relays spread across the two cards. This provides enough functionality for the computer to perform the move 8, set AB and ALU 8-cycle instructions. Taking a closer look at the front of the lower card on the right, we have the first set of status LEDs. The LEDs fall into two groups. On the left is the register load and select group, and on the right is the condition register load group. In the register load select group on the left, there are four yellow LEDs which show the loading of registers A through to D, and below those are four green LEDs which show the selecting of registers A through to D. Moving over to the upper card on the left is the next set of status LEDs. There are three groups of LEDs here. On the left is the sequencer abort group, in the middle is the memory group, and on the right is the ALU group. There's a single LED in the sequencer abort group, which shows when the abort 8 control line is activated. At the moment we're only dealing with 8-cycle instructions, but further abort LEDs will be added here later. In the memory group is the I to B or immediate to bus LED. This is lit when the controller is requesting that the lower 5 bits of the instruction register are gated onto the data bus. Finally, in the ALU group on the right, the 3 bits of the ALU function code is shown when appropriate during ALU instructions. Moving further up the card, we have two of the 3 instruction relay groups. The 5 lower relays handle the ALU instruction, and the 3 relays above operate the set AB instruction. Moving further up the card again, we have the single abort relay. This signals to the instruction relay groups to set their abort signal at the appropriate time so that it is latched into the sequencer. Again, as all 3 instructions are 8-cycle at the moment, each group will activate the abort 8 line. To the left of the abort relay, you can see there's quite a lot of slack in the wire wraps. This is where further relay groups will be added later on, and the slack will make it easier to solder in the sockets and headers and to cut in the wire wraps as required. Heading back over to the lower card on the right, we have the remaining 3rd relay group, which handles the move 8 instruction. This will be expanded to the right later when the move 16 instruction is added, and further relay groups will also be added below this. When all the planned instructions are implemented, both cards will be pretty tightly packed with relays. At the bottom right of the card are the board interconnects. This allows the required signals to pass between the upper and lower cards. For now, there's 5 blocks in use, plus 2 power blocks. Starting bottom right, we have the power connector, and to the far left the accompanying ground connector. Above the power connector is a sequencer pulse connector. For now, just pulses C and D are passed between the cards. To the left is the instruction bus lines, where the lower 6 bits are passed through. Above these are the remaining 3 connector groups. On the left is the register load lines. Next is the register select lines along with the immediate to bus line. And finally on the right is the abort 8 line, condition register load line, and the chat line, which instructs the active instruction relay group to activate its abort line as appropriate. All of these connector groups map to the equivalent location on the upper card, effectively transferring the lines that come in on the lower card to the upper card, and transferring the lines that come in on the upper card to the lower card. In this way, the two cards together can access a greater selection of connections with the rest of the computer. Speaking of which, at the top of the card is where we find the upper card connectors, which let the cards talk to the outside world as it were. Going from left to right, we first have the power connector. This is followed by the control and all-important instruction bus, which provides the lower bits of the instruction, which is used by the active instruction relay group to define the exact variant of instruction to perform. Next up is the operation bus. This carries the current instruction class generated by the decoder card, which is ultimately derived from the active opcode held by the instruction register. Finally on the right is the pulse bus, which will carry the time impulses generated by the sequencer cards. Heading back over to the lower card on the right, we've got the next set of connectors. Going from left to right again, we first have the X control bus. There's only one line used on this bus for now, and that's the immediate to bus. Next up, we have the Y control bus, which isn't used by this card, at least not for now. Finally on the right, we have the Z control bus. This is where the register load and select lines for registers A through to D are sent out. There's a surprising amount on these two cards, given there's just 3 instructions implemented at the moment. There'll be lots more instructions to come, but it will all fit on these 2 cards, promise. For now though, I'll move on to giving the control card a test as it currently stands. To make things more realistic, I'll hook up the sequencer from my last video as well, being as the sequencer and control card really are designed to work as a pair. In fact, the sequencer pulse bus doesn't extend beyond the backplane that the sequencer and controller both sit on. So, onto the demonstration itself, and I'm trying something slightly different this time. I've taken 2 videos simultaneously, one from the front of the cards and one above the test board. It was a pain to put together in iMovie, so hopefully it's worthwhile and shows you more of what's going on. In the top left section is a test board seen in previous videos. On the test board, I've rigged up the leftmost button to the sequencer reset line. The dip switches to the right of this to the decoded instruction class lines, the next dip switches to the instruction bus, and finally the button following those to the clock line. Taken all together, this will allow me to operate the sequencer and controller together without needing the instruction decoder card. In the bottom half of the frame is the controller cards on the left and the sequencer cards on the right, both seen from the front so that all the LEDs can be observed. I've added a label strip in the middle to show what each LED represents. Finally, in the top right section is where I'll show more information on the active instruction class. Right, off we go then, and I'll start by turning on the power supply. And to begin with, no LEDs are lit, which is as expected. The sequencer won't spring to life until the reset line is activated to get the finite state machine into a ready state. I'll start by setting the set AB instruction class. As shown at the top right, the set AB instruction is active when the first 2 bits of the instruction code are set to 0 and 1. Here, of course, I'm forcing the instruction class on through the left-hand dip switches. The remaining 6 bits are gated directly onto the data bus when the immediate to bus, I2B, control line is set. I can't demonstrate the value actually being placed onto the bus here, as the I2B relays are on the instruction register card. Nonetheless, let's enter the instruction code to set 0 into the A register. As you can see, the instruction set on the middle dip switches is shown in yellow as 01, 00, 0000. I've also shown an assembler mnemonic representing this instruction. For set AB class instructions, that is LDI or load immediate. This is followed by the destination register, A in this case, and finally the value to load. This is shown in hex here, but could be decimal or binary, although 0 will be the same in all styles of course. With the instruction now set, I can activate the sequencer and then clock through the instruction. We're expecting that the I2B line will be activated and held for 3 pulses, with the load A line pulsed in between. The timing diagram is shown at the top right. I'll play this one pretty slowly to begin with, so you can follow along. That all worked as expected. Note that the control card also activated the abort 8 line early on to tell the sequencer that this is an 8 cycle instruction and it should reset at the 8th stage, ready for the next instruction. I'll now change the instruction slightly so that it loads the B register by setting bit 5. I'll play this through slowly again. That's all I can really show for the setAB instruction for now, but it's all working as intended. Next up is the move8 instruction. Looking to the top right again, you can see the details of the move8 instruction. This is active when the first 2 bits of the instruction code are both set to 0. Again, I force the instruction class on through the left-hand dip switches. The next 3 bits select the destination, and the final 3 bits select the source. As you can see, there's extra capacity in each 3-bit block for future destinations and sources. For now though, you can choose between the 4 registers A, B, C and D. Effectively, with all of the instruction code bits set off, we're requesting to copy the value in register A to register A. In practice, this would actually clear the register's value. Again, I've shown the assembler mnemonic for this instruction, which is MOV or MOV. This is followed by the destination register and then by the source register. As before, I can now clock this instruction through, and you should see that register A is selected and loaded at the same time, but that the select is held on for 2 pulses to ensure there's sufficient time for the load to take place before the value placed on the data bus disappears. If these both happened in a single pulse, there's a risk the select relays would drop before the load relays did, effectively placing a value of 0 into the target register. I'll play this a little faster than before, but it's a lower left set of LEDs you want to look out for. That looked all good. I'll now change the instruction to copy the value on the C register to the B register. Rather than play it slowly, I'll do it in real time. Finally, for this instruction, I'll set up a copy from the D register to the B register. That's also looking good and as intended. I'll move on now to the final instruction class that's implemented, the ALU instruction. The ALU instruction is active when the first bit is set to 1, followed by 3 zeros. As before, I force the instruction class on through the left-hand dip switches. Bit 3 selects a destination for the result, either the A or D registers, and finally bits 0 through to 2 define the ALU operation itself. This 3-bit value is passed directly to the ALU cards, so it's just gated through by the controller as is. Starting with the first and last bit set, we have the ALU instruction for adding the result going to the A register. Each operation within the ALU instruction gets its own assembler mnemonic, and the add instruction is fairly memorable. I'll clock this one through slowly again, as there's more going on than with previous instructions. The ALU function code will be set for 3 cycles, and then within this both the destination register and the condition register will be loaded. All good. I'll now change the instruction to perform the exclusive OR operation, known as XOR. This time I'll set the destination to be register D. As with add, the exclusive OR operation has its own assembly mnemonic, which in this case is EOR. This looks a little inconsistent, but it's selected to match the equivalent in other assemblers used on other computers. Clocking through in real time, we get the following. All as intended. In theory, if the same instruction is left activated, the sequencer would happily cycle through continuously. Later on, the sequencer and controller cards will handle the loading of the next instruction from memory. Although there's no clock card yet, also coming soon, I can clock through quickly to give you an idea of how the cards would look when in full use. So that's it for now. Next job will be to add the new control lines and instruction classes to the display cards and build a black plane that the sequencer, controller and decoder cards will all sit on. Once that's done, it should be possible to enter in single instruction opcode on the front switches and then clock the instruction through. Following this, I'll probably build the clock card and then move on to the memory card, instruction pointer and incrementer. With these in place, it should then be possible to enter and run a basic program. As always, I'll be posting progress on my blog at relaycomputer.blogspot.co.uk, so please do take a look, and I'll no doubt put together a new video on here as soon as there's something more interesting to show.